What constitutes a good regression line? It goes through the mean of x comma the mean of y. That's called the mean point. It probably won't pass through any of the other points, but should be close to a lot of them. And huge gaps between the line and the points concern us, but not minor discrepancies. So we are no longer using that old strategy of finding 2 points and using the slope equation and to find the equation of the line. Okay. What is a residual? A residual of the point is the difference between the actual data value and the data predicted by the model. The value predicted by the model is the point on the line that has that x value. So you're really looking at the distance between each point and the regression line. That is called a residual. Someone asked me yesterday, what is resid? Because they saw it in the list, right? Well, your calculator will calculate all of the residuals for your scatter plot after you create the regression line. So you do the linear regression, the lin-reg, and it makes the line, and it automatically does the calculations of each point and how far it is from the regression line. The residuals that are positive are points that are above the regression line, and residuals that are negative are points that are below the regression line. If you add up all the residuals, it's going to equal 0 because that regression line should minimize the distance between the line and all of the points. This is the same thing that happens with standard deviation once we if we add up the distances from all of the points to the mean, we get 0. So if we add up all the residuals, we end up with 0. So how can we make a calculation with that? We use the square. We square the residuals, and that is why our line is called the least squares regression line, because it minimizes the squared values between the value of the squared distances. A residual plot is a graph that plots the residuals on the y-axis with the x value for that point. Some computer outputs actually use the predicted values on the x-axis. It doesn't change the shape of the residual plot. The residual plot allows us to tell whether a linear model is appropriate. If the residual plot has no pattern, no form, it has no direction, it's just a big random scatter of points, a linear model is appropriate. If you see a pattern and a curve in the residual plot, it means that there's an underlying relationship that we haven't accounted for with the model, and that linear model is not appropriate. So here are 3 residual plots. Of those 3 residual plots, which one do you think has completely random scatter? No pattern. C, right? C would be appropriate. So if we saw a residual plot like C, we would say a linear model is appropriate. What do we see in letter A is kind of a parabolic curve, right? That means the points are above the line, below the line, and then they go back above the line. So there's some kind of curve that our line doesn't account for. B shows inconsistent spread. The points are farther away, but as the x values increase, they actually get closer and closer to the regression line. So they're getting more and more accurate. The model is getting more and more accurate, but it's not accounting for all of it in the lower values, or if it was opposite, the upper values. So this narrowing of the spread, this is inconsistent spread, also tells us that there's a relationship that our model is not accounting for. And when I say the model, I mean the equation. Okay? The model is not the scatter plot. Okay? The scatter plot is a graphical display. The model is the regression equation. Okay, so this one has a pattern. It's a curve. The middle one has inconsistent spread. What we're looking for is no pattern, consistent spread, random scatter. That's where a linear model is appropriate. So you're looking for a residual plot that looks like C. Okay. So the regression line, also known as the model, the regression model, is called the least squares regression line because it minimizes the sum of the squared residuals. So correlation and regression. Consider an example of a mythical college where the correlation between the SAT scores of their freshmen and the GPAs they earn is 0.5. What should the college predict about a freshman GPA of an applicant who is average in SAT score? So it's common sense that if a student has an average SAT score, we expect their GPA to be about average. Because we know that the mean, the average of X and the average of Y, is on our regression line. Okay, will it be exactly the average? No. It's just a prediction, right? Of course, it's going to vary some. But what can we say about a student that is 1 standard deviation above average on their SAT score? Or 2 standard deviations above average in their SAT score? What do we expect a freshman GPA to be? So how far above the mean should we predict the GPA to be? We may think initially, well, if you're 2 standard deviations above the mean on your SAT, you're 2 standard deviations on the GPA, which is not actually how it works. It's unusual for anything to be 2 standard deviations above the mean, right? Only 2.5% of the data is above the mean, so it's pretty unlikely that you're both 2 standard deviations above the mean on your SAT and 2 standard deviations above the mean on your GPA. When we have a correlation of 1, that's a perfect linear relationship. Correlation of 1 would mean yes, if I am 1 standard deviation from the mean on the X, I am 1 standard deviation on the mean from the Y. If I'm 2 standard deviations below the mean on the X, I'm 2 standard deviations below the mean on the Y. So what do you think a correlation of 0.5 is going to tell us to predict if we are 2 standard deviations above the mean on the X, the GPA or the SAT score?
1 standard deviation on the Y.
Right, 1 standard deviation on the Y. So you can say if I'm 1 standard deviation on the Y, on the X, I am R, the correlation standard deviations on the Y. So if the correlation was 0.75, then if I'm 1 standard deviation below the mean, I expect to be 0.75 standard deviations below the mean on the Y value. Okay, so that R is how many standard deviations we expect to be on the on the Y for every 1 standard deviation on the X. That caution that we are using to say, well, we don't really think it's going to be a perfect relationship is called regression. Another place they use regression for in like real world terms is like when you're potty training your kids and they're doing really good, and then all of a sudden they start to regress and they start peeing their pants or going at night. Like that's a regression where they're coming back, right? They're going backwards. They're not progressing as far as you were hoping. So that's another time that I've heard it used. All right, so to write the equation of a best fit line in the original units, we need to only know two things: the mean point, and the slope. If I know the mean point, if I know the slope of the line and a point it passes through, we can write an equation. That's algebra. That's algebra 1. That was a long time ago for a lot of you. Okay? We can use this equation to find slope from the summary statistics. The variable we are going to use for slope is no longer m. We use b1 for slope. M would get too confusing with mean, right, and mu and all that. So we use b1 for slope. And this is the correlation times the standard deviation of y divided by the standard deviation of x. Should be pretty familiar because our slope equation was the change in y divided by the change in x from algebra 1, right? From pre-algebra. y2 minus y1, right? That's finding the change in y over x2 minus x1. That's the change in x. But statistically, the change, the variation, is our standard deviation. So we can take this correlation times the standard deviation of y divided by the standard deviation of x, and that gives us our slope. We use b naught as our y-intercept variable. In the calculator, this is a and b. Okay. In the calculator, a is your b naught, your y-intercept, and b is your slope. In the textbook on the AP exams, you're going to see b naught plus b1x. The regression equation, this slide got all messed up when I imported it. We want to write our equations with meaningful variables, not x and y. So if we're talking about the predicted GPA plus the y-intercept, the slope times the SAT score, we are actually going to put the word for our variable in our equation. That way we don't have to define what x and y are later. So it's GPA with this little hat on top of it. We say GPA hat, because that means this is the predicted GPA. We know that it's not going to be exact. Our equation is just trying to make a prediction based on the data. So we make sure to clearly identify the fact that we know this is just a prediction. This isn't the actual GPA. So that's called GPA hat. That's how we say it. And it means the predicted GPA or y value. Now our general equation, because we can't read this weird symbols that get imported into my equation, we already said that b naught is the y-intercept. And our general equation is y hat equals b naught plus b1x. Predicted value for y is equal to the y-intercept plus the slope times the variable x. Very similar to mx plus b, we just reverse it and give it some new variables. And we're going to use words. Okay? If we're talking about height, we're going to say male weight hat equals whatever plus whatever times male height. We're going to use the words for the variables, not just x and y. Okay? So I apologize for this slide looking all funky. Hold on a sec. As we calculate, we need our slope formula. B1 is R times SY over SX. Okay, we're going to dig back into some old algebra here. For A, to find my slope, what is my R in A here? 0.5. Times my SY, which is 3, over SX, which is 2. So that's 3 times 0.5 is 1.5 divided by 2. 0.75 is my slope. Yeah? So if I know the slope and a point, 10, 20, where'd I get 10, 20? My only point that I know for sure is on the line is the mean of x, the mean of y. So that's 10, 20. How do I find the y-intercept from this information? I'm hearing ideas. Plug in x and y, right? Yeah. We plug in x and y in the slope and we can find the y-intercept, right? So y1, I'm pointing to it like you can see it. I'm going to plug in the mean of y. I'm actually going to do y bar equals b naught plus b1 times x bar, which is 20. Equals b naught plus 0.75 times 10, the mean of x, right? Now we'll work a little algebra magic here. 20 equals 0.0 plus 7.5 minus 7.5, and 12.5 equals b naught, right? 20 minus 7.5? Yep. So y hat equals 12.5 plus 0.75x. That's my equation. Okay, so take a second and do, forgot to record. So we get that for our slope. Our mean of y is 7.2 equals b naught minus 8 times 2. Right? The mean of x, the mean of y go in as our x and our y. So that's plus 16, right? So 23.2 equals b naught. And we get y hat equals 23.2 plus, minus 8x. Okay. All right, so part C. What if I know some of the information, but not all of it? Can I find my standard deviation of y? Can I find the mean of y if I have the information I'm given here? Oh my gosh, thinking. All right, so let's talk first about the mean of y. How can I find the mean of y?
Plug in 6, right?
6, the standard deviation. Plug this.
12.
Plug in 12. Plug in the mean of x into the equation, and that should give me the mean of y, right?
Yeah.
Okay, so y hat equals 200 minus 4 times 12.
158.
200 minus 48, 152. So, it's not y hat, it's y bar. Because when I plug in the mean, I get the mean. So I get 152. Now how do I find the slope? B1 is r times sy over sx. I like to write the equation with all the variables in it over and over again on every problem. By the time you get through, you'll have it memorized. This is one of the equations that will be on your formula sheet. Okay, you do get a sheet of equations on the AP exam. Yes?
Wouldn't you just have -4 equals
So I just use my equation, plug in what I know, solve for what I don't know. So that's negative 24 equals negative 0.8 times sy. Divide by negative 0.8. And I get 30. So sy equals positive 30. Okay, so we can use these equations. How about if I want to find the correlation? Here we have the correlation missing. What's my slope?
Could you scroll up again so I can see the full tables of present? This would just be another plugging in and solving as we just did.
Right, we're going to plug in and solve for what we don't know. So my slope is what? 50, right?
Yeah.
The slope is the number in front of the x. That doesn't change. The number in front of the x was the slope in algebra 2. The number in front of the x was the slope in algebra 1. The number in front of the x is still the slope. Okay? So slope 50 equals r times sy, which in this case is 100, divided by sx, 1.2. Yeah?
Yeah.
So 50 times 1.2, 60 equals r times 100, divided by 100, r equals 0.6. What do you do if you're solving for r and you get a number bigger than 1?
No solution?
No. Check your work. Right? Check your work, because r can't be greater than 1. So if you're solving for it in a situation like this and you get r is 1.3, you did something wrong. Okay? You probably put your x on top instead of your y. Right? And then if I want to find again, the mean of y, I just plug it in. Negative 100 plus 50 times 2.5. Negative 100 plus 125. Y bar is 25. Okay. So we can use our equations, kind of getting you familiar with algebra again. For some of you, it's been a while. So sometimes they're going to give you the slope and the y-intercept. They're going to give you what's called r squared, which is the correlation squared, right? And you're going to have to write the equation. You're going to have to interpret some things. So I just want to talk a little bit about what this information is. We're given the scatter plot here. We can see it's the number of wins and the home attendance for that game. We looked at the relationship between the number of wins by American League baseball teams and the average attendance at their home games for the 2006 season. Here's the scatter plot, the residual plot, and part of the regression analysis. So here's our scatter plot. Does it look straight enough? Sure. Here's our residual plot. Does it look randomly scattered? It kind of has some increased spread, doesn't it? Which we see here because it's getting more spread out, right? These points are farther from the line than these two little guys here. But if you looked at the graph from here over, it's not so bad. Okay? The problem is 60 teams or 60 wins seems to be pretty low for a team, right? So is a linear model appropriate here? That's the first question. Well, the residual plot has some inconsistent spread, so linear model may not be appropriate, and we can say that. But what is this information given down here? Okay, and we're going to look, I'm going to give you a worksheet probably Thursday, and we're going to look at the whole regression output, what it means. We're going to highlight and identify everything. But this is something like a snapshot that the book gives you, okay? So what we have here is dependent variable. Is dependent variable x or y?
Y.
It's the y variable. Is home attendance. So y is home attendance. It tells us the r squared is 48.5%. It tells us the constant. What do you think the constant is? Do you think that's the slope or the y-intercept?
Y-intercept.
The y-intercept. I thought I heard it, but it's very quiet sometimes. So the constant is your y-intercept. And the winds is what? Yes, this is your x variable. And that means this is your slope. Okay. So it's giving us the equation. And we're going to write home attendance, the big hat on it, equals negative 14,364.5 plus, because the x is, or the slope is positive, 538.915, and my x variable is winds. That's how we would write our equation from this regression output. It's literally giving it to you. All you have to do is put it in the equation. Okay? Questions on that? Some of the questions it's asking is, do the residuals show any pattern worth remarking on? Well, yeah, we do see the inconsistent spread here. That makes us think that maybe the linear model is not appropriate. Based on the scatter plot, it looks straight enough. Then it asks, the point in the upper right of the plot is New York Yankees. What can we say about the residual? This point here is the Yankees. What can we say about that residual? The residual on a graph is the distance between the point that you would get on the line and the actual data point. So is this positive or negative?
Positive.
It's positive because it's above the line. The residual is the observed, the actual minus the line. So when it's below the line, it's negative. Can we say it's the largest of all of them? Yep, it's definitely the largest residual. Here it is again on the residual plot. Okay, so it's the largest residual. And we'll talk about the meaning of r squared in context. But what would the r be if the r squared is 48.5? How can I find that? Do I want to do the square root of 48.5 or do I want to do the square root of 0.485? Okay. I want to do the square root of the decimal form of that r squared. Okay. So the square root of 0.485 is 0.696. So r squared is 0.485. So r is the square root of r squared, which would be 0.698.